Hello, good afternoon, everyone. Am I audible? All right. Okay, so it seems like I am audible right now. Thank you very much for the thumbs up. Good afternoon, everyone, and welcome to our first session of SIICaP Lakbay Kalawakan inside the control room, outward to space. Thank you for joining us today. My name is Joe Briones. I'm one of the information officers of the Philippine Space Agency. In our previous Lakbay Kalawakan webinar series, we introduced the basics of space mission control and ground segment operations. In this new chapter, we will be taking a look beyond the foundations and into the far reaches of outer space. In Lakbay Kalawakan inside the control room outward into space, we will explore a fascinating variety of space missions, such as satellite internet constellations, rocket launches, space weather and environment, interplanetary exploration, and more. Today is part one of this webinar, where we will unravel the fascinating world of communications satellites with our esteemed guest speakers, two industry experts in the field of satellite communications. We will discover how the invisible networks of geostationary Earth orbit or GEO satellites enable critical global communication from space, and how low Earth orbit or LEO satellite internet constellations are transforming the landscape of internet connectivity.
All right, thank you, Miss Jo, for the brief introduction of today's webinar. Hello, everyone. I am Draylan Gentrible of the High Performance Computer and Information Systems Division, and I will be your co-host for today. We would like to acknowledge our participants from various local government units, national government agencies, colleges, and universities. Just a few reminders for anybody on the webinar. Kindly mute your microphones and please turn off your cameras when not in use. And please turn off. And if you have any questions for our speakers, please do not hesitate to raise your hand or type your questions in the Q&A section of the Microsoft Teams.
All right, thank you very much for the reminder. So everyone, please remember the house rules. They're showed on your screen right now. You can take a screenshot of it just for reference. And now to officially start the program, Dr. Ariel C. Blanco, Director of the PhilSA Space Information Infrastructure Bureau, has recorded an opening message for the kickoff of this year's Lakbay Kalawakan.
Magandang hapon po sa ating lahat. It is with great pleasure that I welcome all of you today to PhilSA's SIICaP webinar entitled Lakbay Kalawakan Inside the Control Room, Outward into Space. This afternoon, we have the privilege of hosting two distinguished industry experts who will share their extensive knowledge on communication satellites. Our esteemed speakers will delve into the concepts, operations, and applications of geostationary Earth orbit or GEO communication satellites and low Earth orbit or LEO satellite internet constellations. GEO satellites have played a pivotal role in revolutionizing global communications. Positioned at a fixed point approximately 36,000 kilometers above the Earth's equator, these satellites have enabled a wide range of vital services. One prominent use of GEO satellites is in television broadcasting, allowing for the distribution of news, sports, entertainment, and educational content to millions of viewers worldwide. With their extensive coverage, these satellites also facilitate long-distance telecommunications and secure data transfer. Furthermore, GEO satellites are instrumental in providing internet connectivity, enabling individuals and businesses to access online resources, conduct e-commerce, and connect with others across the globe. In recent years, LEO satellite constellations have emerged as a promising technology in the field of satellite communication. Unlike GEO satellites, LEO constellations consist of numerous smaller satellites orbiting at lower altitudes, ranging from 160 to 2,000 kilometers above the Earth's surface. The low altitude and distributed nature of these constellations offer several advantages and open up new possibilities. One of the most notable applications is satellite internet connectivity. LEO constellations, including OneWeb, SpaceX Starlink, and Amazon's Project Kuiper, aim to provide high-speed internet access to underserved and remote regions where traditional terrestrial infrastructure is limited. With low latency connections and increased bandwidth, these constellations can bridge the digital divide and provide reliable internet access to previously unreachable areas. Today, we have the honor of learning from two distinguished professionals in the field of satellite communications, Mr. Alfred Donald Perez, Director of Satellite Fleet Operations at ABS Global, and Mr. Bala Balamurali, OneWeb's Director for Southeast Asia and the Pacific region. They will guide us through the world of satellite communications, allowing us to explore the technology behind geosatellites and LEO satellite constellations while appreciating the multitude of applications they offer. From enabling global communication networks to revolutionizing internet access, these technologies have transformed the way we connect, communicate, and understand our world. By examining these technologies side by side, we hope to foster meaningful conversations and gain insights that will shape the future of communication and connectivity both within our country and around the world. Once again, I express my heartfelt gratitude to each of you for joining us today for this SIICaP webinar. Let us seize this opportunity to explore the vast possibilities that lie ahead in this field of communication satellites. Maraming salamat.
All right. Thank you, Dr. Ariel, for your welcome remarks. Our first presenter for today is Mr. Alfred Donald H. Perez. He will be talking about geostationary Earth orbit communication satellites from ABS Global Limited. Mr. Perez is a graduate of Bachelor of Science in Electronics and Communications Engineering from Mapua University. He worked in satellite operation industry for the past 25 years. He has trained in the US and locally on satellite bus and operation. He has handled operations of 7 communication satellites from 3 different satellite bus platforms. And he has worked in telecommunications industry for 7 years, handling data fund satellite networks. And Mr. Perez is currently the Director of Satellite Fleet Operations in ABS Global Limited. So let's all welcome Mr. Alfred Donald H. Perez. Good afternoon, sir. The floor is yours. Sir, nakamute po ata kayo.
Yeah, sorry about that. Yeah, again, good afternoon, everyone, and thank you for giving me this opportunity to share whatever I can share based on what we had experienced or been doing in our field of work. Okay, let me just share my screen. Can you see it now?
Yes, sir.
Yes, sir.
Okay. So I'll be describing to you geocommunication satellite from the perspective of the satellite operator. So I'll give you a brief description of the satellite and what we do here at the station. So first of all, just a recap. So what's an orbit? An orbit is a regular repeating path that one object in space takes around another one. So this is the path that satellites takes. And if it orbits around the planet Earth, then it's a geocentric orbit. So orbits can be also classified in terms of if it's circular or elliptical. Circular has an eccentricity of 0, and elliptical orbits have the eccentricity of less than 1. And low Earth orbit, as the director, Dr. Blanco mentioned, these are orbits or geocentric orbits that with altitude of below 2,000 kilometers. Above that, we call the medium Earth orbit, which are geocentric orbits ranging in altitude from 2,000 to around 35,700 kilometers. And above that is the geosynchronous orbit, which we will discuss later. So geosynchronous orbit is in an altitude of around 35,000 kilometers. It has a period that equals the sidereal day, which is on the rotation of the Earth. So it will look, but that's why it's geosynchronous. It's synchronous with the rotation of the Earth. And there's also the high Earth orbit, which are geocentric orbits that are above the geosynchronous orbit, above 86,000 kilometers. So next is a special type of geosynchronous orbit, which are the geostationary orbit. This one is an orbit that has a zero inclination, so the object seems parked over the equator. So if you can see the satellite, it appears that it's not moving. It's just following the Earth there as it rotates. So in comparison to a non-geostationary orbit, some geosynchronous orbit have an angle of inclination. So if you're looking or right below that, if you're standing on the equator right below that satellite, the satellite will appear like moving in a figure 8 path. So what are the applications of satellite? So especially in the geosynchronous orbit. So we have geopositional system or GPS, but these are mostly in the LEO orbit. And we also have satellite imagery application and weather monitoring application. Well, all of these are mostly in the LEO orbit. And the geosynchronous orbit, there are also some weather satellites that are flown there, especially from the government or US government side. But for today, we'll be talking about communication satellites. So what do communication satellites do? As us, we are operators, we can provide service to telcos. We can also provide services to broadcasters. We can also provide services to private networks that runs their own data communication or IT or broadband networks. We can also provide service to other service providers like VSAT operators or other network operators that distribute the same service or similar service to the same industry. Okay, so next we talk about the coverage of the satellite. So the coverage of the satellite commonly termed as footprint. It will depend on the longitude or location of the satellite. So it cannot cover if your satellite is on the other side of the world. So in order for you to avail provide service, the footprint has to be over that area, and the satellite should be logically be above that area. So the coverage also is dictated by the shape of the footprint and also, of course, the frequency band that's being used. So common bands are C bands, KU bands, and nowadays they're also talking about KA bands and some, of course, L bands, especially in the lower orbit. So frequency band is very limited. So it's a we need to think of ways on how we can expand the use of these frequency bands. So other ways of doing that is by frequency reuse. So for example, for this, you employ a technique where you can polarize the signal, the RF signals. So you can split it into, in this case, linear polarization. You can split a spectrum. One set is transmitting the horizontal polarization, and the other is on the vertical polarization. So for this spectrum where you have around 500 megahertz of spectrum, you're now doubling your capacity. So that's a very efficient use of your frequency band. You're now doubling your capacity just for implementing and polarizing your RF signals. And the other technique is when you employ footprint or additional footprint or contour shaping, like in the sample here. One satellite is transmitting in multiple beam or footprints. I'm just showing here two, but you can have whatever. You can have 3, 4, 5 different footprints, and for every footprints, you can use the same set of frequency band. So, just in this example, for the same spectrum, you're using the frequency 4 times. So that's a lot of gain in terms of frequency spectrum efficiency. So next I'll be describing to you the spacecraft itself. So the different functions of the components of the satellite and how we operate it. So first would be the power subsystem. This is the primary source. This function subsystem provides the primary source of spacecraft. So normally this is a solar power energy that's being converted to electrical energy to supply all the components within the spacecraft. And it also provides a secondary source of energy, which is typically a battery. Normally, this is used for certain or seasonally in certain occasions, like for example, during eclipse season, since we are in geosynchronous orbit, there's a time of the year when the Earth, the Sun, and the satellite are all aligned. And in that case, the Sun or the Earth is blocking the Sun from providing sunlight to our solar array. So that's when we use the batteries. Excuse me. For the thermal subsystem, this is the subsystem that keep the satellite components within operating temperature range of the units. Since space is so robust, meaning we need to make our components robust, but since the space is has a very wide temperature range, it can be so cold if you're under the shade, or can be too hot if you're under the sun. So you need to control the temperature there. And this is done by using thermal blankets. The OSR is an optical I forgot. It's an optical reflector and also the heat pipes. Now the heaters, we also use that in case if the satellite is under the shade, you need the heaters too to control the temperature. And the thermistors, these are the temperature sensors. So you need a control loop in order to keep the temperatures. And those are optical solar reflectors. That's how I remember. So this looks like mirrors. So normally these are installed on the outer side or outer face of the satellite. So this keeps most of the sunlight radiation out or reflected back into space. So the temperature is controlled within the satellite. And the next subsystem is the attitude control. So attitude control, this is the main controlling function or system that controls the pointing or orientation of the satellite. So this is composed of sensors and actuators. So for sensors, it either uses an Earth or Sun sensor or star tracker. And or gyro, and then it controls this the attitude of the satellite by using momentum or reaction wheels or even thrusters. So it steers the satellite's orientation, so it keeps on providing a stable footprint on the surface of the Earth. For satellite computer, this is actually the brain of the satellite. So all the algorithms, all the programs that controls the other subsystem is installed here. So this is the housekeeping function of these. It does the housekeeping function within the satellite. And besides that, this is also where the processing of all the commanding and telemetry or data that's being transmitted to and from the satellite from the ground station. And it also handles the safing functions of the satellite, meaning most of the satellites now are automated, meaning if there's any failure on any component, it already has a program or codes within the system, which is inside the satellite computer, that would switch over to a backup unit. So it saves the the satellite from going to an unrecoverable situation. And next will be the mechanism. So, well, the mechanisms of system, these are the mechanical parts that control the hardware of the satellite, which are the solar array drive, not the solar array itself, but the drive, which is the mechanism that holds the solar array and rotates the solar array so it will follow the sun. And we also have antenna positioners. Normally, these are used for calibrating the position of the antenna, since these antennas are folded and stowed during launch and deployed after it reaches position or after it separates from the launcher, depending on the program. You need to revalidate the position, check if it's pointed to the right foot, say right direction. So you use the antenna positioners to readjust these. And sometimes, depending on the mission of the satellite, it gives there are some capabilities to reorient the antennas itself, meaning you have a wider range of adjustment, so you can repoint the antenna or the footprint on the surface of the Earth for other purposes or for covering other areas. And then the next system is the propulsion, which produces the force and torques to modify the satellite orbit and to support attitude control. So earlier for the attitude control, it's controlling the attitude, meaning the tilting or panning of the spacecraft itself. But here, the propulsion system provides or supports the control of the orbit, meaning how it moves around the Earth. So it's also used for attitude control because some spacecraft are still using chemical thrusters to control the attitude, but some spacecraft don't use that. Some are just relying on other actuators to control the attitude, like reaction wheels. So for propulsion system, it also includes the thrusters. Some spacecraft uses chemical thrusters and some uses electric thrusters. So samples of the electric thrusters are the arc jets, the plasma thrusters, and the xenon thrusters. And the next subsystem will be the TCR, or the telemetry command and range. So later on, we'll touch on this a little more. So these subsystems takes care of the communication between the satellite and the ground system, or the controlling ground system. So telemetry refers to the information or the signal, information within the signal that goes from the spacecraft to the ground station. Command refers to the opposite direction, meaning it's the communication from the ground towards the spacecraft, and it's called command because normally when you do that, you're reconfiguring or inquiring on the spacecraft status. So that's why it's called command. And range is for used for determining the position or the distance of the satellite from a ground station. So later on, we'll discuss that. And lastly, this is, well, some will say this is the computer is the heart, but this is the main function of the satellite. So that's called the payload. So in our case, our main function or for the payload is for providing communication. So that's why it's called a communication satellite. So this comprises of uh, uh, receivers and transmitters that provide communication or to retransmit the signals that's coming from the ground. Now, one common term that you'll probably encounter is the term transponder. So, and that refers to the communication channels on the satellite. So, what really is a transponder? So, transponder is not a single unit on the spacecraft, but it's actually a path, a complete path between the receiving antenna up to the transmitting antenna. So, a transponder is composed of the receiving antenna, the receiving LNAs, the receivers, and a series of filters and channel filters, which breaks down the uh, spectrum into channelized or smaller spectrum, so it can be amplified individually. And then it passes through a pre-amplifier or channel amplifier. So the main function of this channel amplifier is to boost up the signal that can be sensed by the main amplifier. So the main amplifier then boosts it further, much stronger, so it can be transmitted at a power level that is receivable from the Earth. So a transponder is a whole path. Like for this example, you can see 3 transponders. So one path over here, one path in the middle, and one path over at the bottom. So that's a transponder. It's not a single unit, but a combination of units to make a path. So in this example, I'm just showing 3, but there can be multiple transponders. Say, for example, just for this path, this can be further split into 3 or 4 further sub-channels. So that's each of those is individually a transponder. So next would be the ground system. So how do we control the spacecraft? So of course, we need the ground system to communicate with the spacecraft, to this geosynchronous satellite. So as a typical setup for a ground system or similar to also the spacecraft, we have an antenna, the receiver, the down converters. The down converters convert frequencies from RF to IF, and we have the receiving baseband unit. This baseband unit is very well for satellite control. This is kind of the modem. If you're familiar with modems in in your homes, when you have 5 internet connections, you have modem routers, right? So this is like the modem routers for satellite control. So it converts all the signals from RF and from IF and converts that to modulated or converts that into digital packets. And on the other path, when we need to send data packets or commands to the satellite, it passes through the same baseband unit, up convert that to the RF range, RF spectrum, and amplify that before being sent out to the satellite. Now, of course, these data packets are now being then distributed to our internal network. So we have network different computers and different functions. So first of all would be the satellite control and monitoring system. So this processes all the information coming from the spacecraft and also process the commands that being sent from the control center. So this is where our satellite controllers will stay and uses the satellite control system and monitoring system to command and receive telemetry from the spacecraft. We also have flight dynamics and planning system or softwares. This is used for planning the orbits or controlling the satellite orbit. And we also have dynamic simulator, which is as an exact a copy of the software on the satellite. So before we transmit anything on the spacecraft, we always try it first with the simulator, so we're sure we're not going to damage or do something that's unnecessary on the satellite. And of course, you need people to control all of these. So we have engineers that plan out the next maneuver and using the simulator as well for reconfiguring the satellite, and the satellite controllers who are doing all the commanding to the spacecraft. So it's only through the satellite control center that we can command to the spacecraft. Although the engineers can access these softwares or systems, they are only on a kind of a read-only mode. So they can only get or collect information, but they cannot do the commanding. All the commandings are done from the control center. And just to show you what we have in Subic, this is how it looks like if you're looking through Google Earth. So this is our facility in Subic, and this is a snapshot of our control center in Subic. Now, how do we monitor a satellite? So, well, we monitor it, but of course, looking at the telemetry. So we have daily checks, which normally we just check the statuses of the configuration of the satellite, the attitude, the temperature and power, and time references as well. We also have weekly activities, especially for maneuver planning. We also do temperature and power trending. So we have to check the long-term trending, not just the instantaneous temperature and power, but also how it behaves or where is it going. So we can do the necessary adjustments if need to. And we also have monthly subsystem check. So it's more trending. So we check all of the subsystems where are the trends going to, and so we can react before anything wrong happens on the spacecraft. And we also have kind of a semi-longer activities like for eclipse operation, for seasonal reconfiguration, like adjusting the reference clock or the reference for our orbit determination. And also we have some occasional work, say, for example, for anomaly event investigation. Well, anomaly is not really a bad word, but anomaly is, as defined, is anything that's outside or outside of the norm. So it could be just a benign thing, but still we need to investigate before anything big or a problem arises. So normally we'll just create traces, plots of the telemetry, and establish the pattern, and as long as the patterns remain the same, then circle. So normally you just spend more time on the initial first few weeks or days, analyze what the patterns are. So once you understand all the patterns, then you can just use it as a template. So as long as the pattern remain the same, then everything's normal. But once you see something unusual or different from that pattern, then we need to investigate. So most of the time, 95% of the time, it's nothing. It's just a seasonal change. And of course, besides the spacecraft itself, we also need to keep the orbit of the satellite, or we call it station keeping, which is the control process required to keep the satellite within a stationary orbit. So what causes the satellite to deviate from its position? So satellite orbits perturbed by the Earth's triaxiality, which is because the Earth is not a complete perfect sphere. So it appears to have three center of masses. So that that three center of masses gives a different gravitational pull. So it affects the position of the satellite or the orbits of the satellite. And also the lunar and solar gravitational axis from the moon and the sun, as it as the Earth rotates or revolves around the sun, the satellite is also exposed to different gravitational pull, and especially for the moon, where it revolves around the Earth every 4 weeks. So it also perturbs the orbit of the satellite. And there's also the solar radiation pressure from the sun. So you can imagine this as like a wind, a blow of strong wind, or very very weak wind that's slowly pushing the satellite uh, away from its orbit. And also the onboard thrusters, it also perturbs the orbit of the satellite because there could be some misalignment, or you cannot just install it perfectly. So there could be some contribution or unintended contribution on the different axes of the satellite. Or sometimes, since thrusters can be used for multiple purposes, eh, it's intentionally tilted from two different or three different axes. So it will have contributions every time to other axes that uh, it was not intended for. And so in order for us to keep the satellite in place, we do the north-south maneuvers and east-west maneuvers. So normally, we keep the satellite within a 0.05 degree position, or which is 0.1 degree in longitude and zero point 0.1 degree in latitude. So you will not, if you will see the satellite, it will rotate around this area, slowly moving to a side or two. So in order to keep that satellite within that box, we do north-south and east-west maneuvers. So for north-south, we that's for correcting the inclination, which is the more of the latitude boundaries. And the east-west maneuver is to control the drift and eccentricity, which is dictated by the east and west boundaries of this box. So in order for us to determine the orbit, well, in order to maneuver, you need to know where you are, where the satellite is. So we do that through orbit determination, and orbit determination is done by collecting data through tracking and ranging. So what do we mean by tracking and ranging? For tracking, we track, or you collect the azimuth and elevation angles from the tracking Earth stations. We collect those and uh, feed that to our flight dynamic planning software. And in addition to that, you also collect the range or the distance measurement between the satellite and the ground station. Remember the TCR subsystem? This is where that is used. So with a combination of this and the number of data measurement, we can determine the satellite position or satellite orbit. So here I'm showing here the frequency of how often we get or collect information or tracking and ranging information. So here, almost every 30 minutes, we collect this information to get a more accurate this orbit. If you do a less frequent collection and sparingly, or probably not even a uh, controlled or consistent pattern, it might give you a inaccurate orbit. Here I indicated RF because this is traditionally what's being used, but now these days they're also using optical telescopes. So it's similar, but they don't need to do ranging anymore. So what they do here is using powerful telescopes. They they collect the position of the telescope when they are looking at specific satellites. Well, these are very, I don't know really how it works, but they're very efficient because one telescope can see multiple satellites at a time on, well, they can assess it, uh, multiple satellites at a certain time. And here at the end of, or some special occasions or change of mission, we do this, what we call the orbit and relocation. So what is relocation? Which is moving a satellite from one longitude position to the other. And this is dictated by a mission change. Probably uh, the satellite already has been replaced and is still usable. Probably you can use it somewhere else before, instead of just junking it. So what we do then is we need to prepare when we do relocation. So we need to coordinate with other satellite operators. And we do that because we don't know what they're doing as well. So we need to communicate to them our intention, so we won't smash into our own satellites against theirs. And we also need to coordinate in terms of this RF spectrum to be sure that our TTC carriers will not interfere with them, or nor if they are also using that frequency, that we can use our, or we can still get in touch with our satellite. So that's important because we need to have a 100% contact with our satellite while it's relocating. And of course, we need to verify that the TTC antenna coverage. This refers to the ground station. So if you're relocating from one or farther longitude position, you need to make sure that you have enough coverage from the antenna. If you're moving from one side to the other, you need to get or rent or lease other antennas so you can have a continue to communicate with the satellite during the relocation. I have a colleague of mine shared this animation from YouTube, so I think I should share this with you. So it has no sound, so I'll just comment on what's being done here. So here, increasing semi-major axis means you raise the altitude of the satellite. So here it made one pulse. It raises the altitude on the opposite side, and the second pulse, that evens out the altitude. So here it started from a lower altitude or geosynchronous altitude and went a higher altitude. This is for drifting a satellite or relocating westward. And a third pulse to bring the altitude back down, and a fourth pulse to control the eccentricity. So you'll see the spacecraft now going down to geosynchronous orbit, and as it goes down, it will seem still. it will look at its top. Now, from moving the spacecraft from west to east, it's the other way around. You decrease the altitude. So here from geosynchronous, you do the first burn, second burn to circularize your orbit, and now it's on lower orbit, lower altitude orbit. Now the satellite will appear drifting to the east. And it will now start to do this, what we call a stop burn. So it will start now to go back to geosynchronous orbit, geosynchronous altitude, and then it will seem to stop in that position. So when the orbiting, it's similar, but it says it only uses 2 pulses, but in reality, it's safer to break it down into multiple pairs. 1 pulse, second pulse to circularize the orbit, and now satellite is on a higher altitude, which is at least 200 kilometers. Since it's at a higher altitude, the spacecraft will drift westward. And that's the graveyard of satellites that had reached its life, end of life. Okay. So that's the orbit. And then lastly, we need to check our neighbors. So we, as operators, we have what we call the space situational awareness. So we monitor the space debris, not only our neighboring satellite, but all the debris around us. So there were some occasions, like back in 2009, when a abandoned Russian satellite collided with Iridium-33. So this is in LEO, and that created a lot of almost 1,800 debris. So that's a lot. So in order for us to do that, we subscribe to US Space Force, who shares the position and orbital elements of all the debris that they track. So this is open to, well, they control it. So if probably from the government, you can subscribe to this, but for individual persons, I'm not quite sure, because they will check who's subscribing to them. And of course, we also check the space weather, which is the space environment, not the Earth's environment, especially for solar radiation or sunspots, which affects the solar radiation, and also some electrical increase in electrical particles. And that's all. Thank you very much for listening.
Thank you very much, Sir Alfred Donald Perez, the Director of Satellite Fleet Operations of ABS Global. Let's all give him a warm round of applause, a virtual applause, please. Thank you very much. All right. Okay, it seems like we have a lot of questions from our audience, both here on the Teams meeting and also on our YouTube channel, where this webinar is being live streamed right now. So, Engineer Perez, are you ready to answer the questions?
Okay, I'll try to answer if I can.
Okay, so the presentation earlier by Engineer Perez of ABS Global was very extensive. It talked about communication payloads, satellite subsystems, ground systems, satellite health monitoring, station keeping, orbit determination, relocation in the orbit, and even touched a bit on space situational awareness. So these are very relevant topics for us today. And we have one very interesting question from our audience here on Teams. What is an interesting challenge or discovery that you have encountered in your years of experience operating GEO satellites?
I'm not quite sure what the person's referring to, but probably he's referring to the challenges that we experience in operating satellite. So probably the the challenge here is given that we are using American satellites, manufactured satellites, there are some restrictions on what information that can be provided to us. I failed to mention earlier on how to, when we're monitoring the health of the satellite, how do we do that, or how did we know or learn how to do that? Just like when you're using a new gadget, diba? What comes with your new gadget? There's a user's manual, diba? And the user's manual, what's normally written in the first few pages? Kalagay doon is what? Read first before you use your gadget. So ganun din sa amin. So when we receive the satellite, beforehand, we receive documents, probably around 3 or 4 binders, 3 inches thick of documents that we can read on so we can learn how to operate the satellite. So although there's a lot of information there, this is very useful for normal operation of the satellite. But during problems, if there's something unusual happening on the satellite, we need to go back to the manufacturer. It's not there. So that's why we monitor the trend, we monitor the health, so we can react or kind of act before anything bad happens on the satellite. So what I'm trying to say is, since the U.S. government is kind of satellites is being controlled by the U.S. government. It's the information about how all the components are working. So we are dependent on the information coming from them. We cannot directly do it by ourselves because of that limitation.
All right, thank you very much for that answer, Sir Perez. Okay, we have another question also from our MS teams. In your experience, how are satellites in GEO past their lifetime get disposed in space?
Yeah, as I presented, we put them in a graveyard orbit, which is higher than geosynchronous, which is mandated, not really mandated, but recommended by the industry. So that the slot or the orbital slot, geosynchronous slot, can be used by others as well.
Yes, thank you for mentioning that there are industry standards and for clarifying what is done for GEO satellites past their lifetime, especially since satellite debris or space debris is a very, let's say, a contentious topic that is rising recently.
Yeah.
Okay, we have another question also from our teams. This might be something that Philsa can also answer. But since we're talking about satellites, LEO geotypes, which government agency is focusing on NTN or non-terrestrial networks that will augment the signal coverage of the Philippines, which is an archipelago?
I think that's beyond the satellite operator. It's more of a
It's a
government
regulatory
agency.
question.
Yeah.
All right. May I ask somebody from PhilSA team to answer? Probably Dr. Israel Bautista. Is he here with us today?
Joe, Hi, Sir Alfred. So for that question, well, mainly the Department of or the ICT is tasked to lead the charge, and of course, the Philippine Space Agency is supporting any efforts towards removing the digital divide within our country. We are actually we also have this project, the Incentivize, if our webinar joiners have heard of it, which we are where we are utilizing this low Earth orbit satellites to connect these geographically isolated areas to the internet. So yeah, so the ICT feels USAID. They have this program Beacon. Uh, so they are the ones who are trying to solve this issue.
All right, thank you very much, Doc Izzy, Doc Israel. So yes, it is under the mandate of the DICT, and PhilSA is in support of these mandates, especially on the space side of things. And for our listeners out there, you may visit the Incentivize project page that is on philsa.gov.ph. One of our chat people will be posting the link on the chat on our Teams and on YouTube. In case you want to read more about it. All right, we have another question from our YouTube viewers, Sir Perez. This was about the video that you showed earlier. So is there a danger for the satellite to hit other satellite or debris when it is moving during the pulses?
Yes, there is. That's why you need to be aware of the debris. And that subscription to the US Space Force is very important. And that's also important to communicate with the other operators. So months or weeks before we do any relocation, we already broadcast our intention and distribute it to all the other operators that we know, so they can respond to us and we have enough time to readjust our plans.
All right, thank you very much for that answer, Engineer Perez. We actually have a question here as well from our PhilSA representative earlier, Dr. Izzy Bautista. He is the officer in charge of the Space Mission Control Operations Division. So there's it's very similar sometimes to what you guys do in your line of work. So his question is actually about the commands. So what are the typical commands sent to the geo communication satellites? Are there regular commands that need to be sent?
Yes, there are routine commands. Let's say, like for example, for maneuver, for loading up the maneuver plans. Nowadays, you can load up multiple maneuver plans on the spacecraft. Back in the old days, everything is done manually. That means all the preparation are done commanded one by one. These days, the new spacecraft, you just have to load up the burn time, when you need to do the burn time, how long the burns, and which thrusters to use. And that's it. Those are the regular commands that we send to the spacecraft.
All right, thank you very much for that answer. So just for the information of the public, the Space Mission Control Operations Division, they are in charge of tasking the sovereign Filipino satellites. So we have Diwata 2, and they're also in charge of processing and downloading the data from other satellite subscriptions that the Philippines has. So yun po yung trabaho nila, and that's why I think Dr. Izzy was very interested in asking that question. Okay, so speaking of the olden days, do satellite cable TVs use geocommunication satellites for their TV shows?
Yes, they do. Well, that's the advantage of satellites, because as we only need to broadcast to one satellite, and depending on the footprint of the satellite, it can be received from anybody, by anybody from within that footprint. So it's just one transmission and multiple receivers.
Right. Thank you very much for that. I think we have two more questions that we could address. These are questions sent on our chat box. So this is a question from Jonalie Alvarez, one of our attendees here. What are the typical satellite types that you normally control? In your case po, sa ABS, weather satellites, communication satellites, or any other satellite types?
No, we're only controlling communication satellites. So we have 3 different buses, all are all American buses.
So-
yeah,
Yes, please go on.
we're still currently controlling 5, but we control as much as 7. Actually, I made a mistake. We controlled 8 before, so but they're all similar buses, so falling down into 3 different buses.
Okay, thank you very much for that answer. We actually have 2 more papala additionally. So this is a question from a representative of the USD Region 6, a Ryan Villamor. So good afternoon, Engineer Perez. The Iloilo Ground Receiving Station was inaugurated last March 10 this year. Are there any plans to capacitate the regional offices of the USD related to its use, especially in post-processing the data that it downloads?
Hi, Joe. I think
that's
a question
for
Yes, I understand. So I think this is beyond the scope of Engineer Perez. Also, somebody
Yeah.
from the Space Mission Control Operations Division of PhilSA may want to answer this.
Hi, Joe. So regarding that question, so actually, since the Iloilo Ground Station is still under the Department of Science and Technology, uh, the plans for the utilization of that station is really up to them, not with PhilSA or with ABS Global at this moment. But definitely, PhilSA would be open to doing capacity building activities. So we actually had previous SIICaP and SIICaP Plus activities related to this data processing, right? And we plan to launch more programs in the future related to it. So we hope the Department of Science and Technology Region 6 will be joining us in these future events.
Thank you very much, Doc IZ. I hope we were able to answer your question, Sir Ryan Villamor of the USD Region 6. We can have one last question from our audience. This is addressed to Engineer Perez. So, considering the many activities needed to be executed inside the control room, about how many people are needed for it to be operated, and from what specific fields of work do they belong?
Well, actually, with controlling 5 satellites, or even when we were controlling 7, we just need 2. Why? Because of the modern ground system nowadays. It's very programmable. You can automate a lot of things. So all of the routine operations are done automatically. So all the things that you need to do is just monitor that it's doing it what it is supposed to do. And most of our staff are from the ECE field. We also have we had before from the EE graduates from EE, but as long as you have knowledge of a few of electronics, I think it's okay. We actually we were open before to accept graduates from the physics, especially for orbital dynamics. Yeah, so it varies, depends on your interest.
All right, thank you very much for that. And I guess it's similar as well in the setup here at the Philippine Space Agency. So the Mission Control Operations Division also has people from the fields mentioned, ECE, EE, and also a lot of people from the field of physics as well. They're the ones doing the tasking and also the data processing of these satellites. So I guess I'm so sorry to our audience. We don't have enough time. If ever, Sir Perez, you could answer the questions that are in the chat through chat. You could type out your answers as well. But that is all our time for our Q&A for Engineer Perez. So thank you very much, sir, for accepting our invitation to speak at this event, for the informative presentation, and for answering all the questions that were raised earlier. Thank you very much, and let's all give him again a warm round of applause.
Thank you too for the opportunity.
Thank you very much, sir. Okay, so we can now proceed to our next presentation, and this will be coming from Mr. Bala Balamurali. He will be talking about OneWeb's low Earth orbit, or LEO, satellite internet constellations. So Mr. Bala is OneWeb's regional director of market access and business development for Southeast and East Asia, which is a high growth region for OneWeb. Low Earth orbit satellite connectivity is a key option, particularly to extend existing networks into harder to reach locations for governments and mobility industries such as aviation and maritime. So with his over 15 years of experience in strategy and business development in satellite communications in the Asia Pacific region, Bala leads OneWeb's business development and market access efforts in the region. His previous experiences includes senior regional leadership positions at Inmarsat, PLDT, and Asia Cellular Satellite. Bala is a chartered management accountant and holds an MBA from the Henley Business School in the United Kingdom. Good afternoon, Mr. Bala Morali. The floor is yours.
Good afternoon. Thank you for that. Thank you for that very colorful introduction. I'm sorry I couldn't join the discussion earlier because I was at another meeting and I've just jumped in, but I managed to see Engineer Perez's presentation and questions towards the end, and I'm really happy that a lot of the technical questions have been thrown at him because I'm not the technical person here today. So what I tried to do is to give you an overall sort of perspective of what LEO satellite constellations are about and what OneWeb is doing, and just to give you a brief overview, because I know it's a very big topic, and I can see from the questions that came up, you could probably discuss this for hours, and it's really exciting to see an audience that's very interested in this topic. There was one question towards the end of, before I get started, let me just make this point, which I've been saying quite a bit to Dr. Joel in our earlier meetings, and that is who is responsible for making all this latest satellite technology available for the Philippine archipelago. I think this is a very good question, and I think it really points to what PhilSA can be doing for the Philippines. And I think you have the capability, the expertise, and the drive to get it done. And I really hope one day PhilSA can be driving this for the Philippines, because I think you need it, and you need an organization like PhilSA to drive it. Well, so before I take up any more of your time, I'm just going to show you a quick video, if I can get the screen to present. Hold on a second, if this works. Please tell me if you can see this and if you can hear it.
Yes, we could hear it, but I don't think there's audio coming from the video.
There is no audio coming?
On my end, I don't think I have. I don't hear anything. Can the audience concur, please?
My end as well, I don't hear audio.
Yeah. Right. So I'm just going to try one more time, and if it doesn't, then I'll skip the videos. Still no audio?
Yes, sir, there's no audio. I'm sorry.
It's my fault. I should have tried the trial run you guys had yesterday. So I will hold off the video. It is basically just a high-level introduction to satellite connectivity in general and low Earth orbit constellations. which is what OneWeb is. So let me skip this and I'll go to the presentation. Hold on 1 second, please.
All right, so while Mr. Balamorali is preparing on his end, I think we could post actually a link of OneWeb's website and probably a link to one of the videos from OneWeb.
Yes, I'm actually going to send you the link to that video that I tried to show you. So bear with me. But that's let's do that separately. But let me see if I can just get through the presentation quickly. Can you see my screen?
Yes, sir. We can see it.
Okay. Thank you. So, you heard quite a bit about the geostationary satellite constellations just from the previous speaker. So satellites per se is not new to the audience here. So I will dive straight into LEO communications. As you mentioned just now in the introduction, I've been in the satellite industry for nearly 20 something years. And, I've seen from the very early days when we were so excited about sending few kilobits per second of data via satellite to now to, somewhere in the region of 150 to 200 megabits per second, and people still complain it's too slow. So that it's a huge improvement that the satellite industry has been through over the last 20 years. But what has happened is also the whole world and the demand for satellite connectivity together with regular connectivity has also gone up significantly. So people's expectations have changed, the commercials have changed, the economics of providing connectivity has changed. And so and also the applications for which satellite connectivity is put to use is also changed. Your last question was, do you deliver video to the homes? Direct to home television came from geostationary satellites, and that was good enough because you're just broadcasting. But now in the world of interactive connectivity, latency and reliability and service level agreements and uninterrupted connectivity, all of these things have become very important for the various applications that satellite connectivity is being used for. So, there are autonomous vehicles, autonomous, maritime vessels, airplanes, which all need uninterrupted and reliable connectivity. So we had to come up with something better, something faster and with low latency. And that is basically what LEO communications brings to the world. So LEO, as it stands, low Earth orbit, and the low Earth orbit ranges in the few hundreds of kilometers all the way up to the early 1,200 kilometer range, which is where the OneWeb satellite orbital plane is. So our goal, in the earlier discussions, I also heard the discussion about responsible space. It's a very important point for OneWeb, and our goal, therefore, is to deliver the best in terms of technology that we can provide for reliable connectivity while making sure that we don't leave a mess up in space. Responsible space is something that OneWeb takes very, very seriously. So while we, throw hundreds of satellites up into space, we also make sure that when their mission is up, they leave that area without too much debris, so that everything that we put up into space comes back down without leaving a trace in space. And that's a key goal that OneWeb has in developing its satellites, in manufacturing, launching them, and then bringing them safely back down to Earth, or making them burn up upon re-entry. So those are the main drivers behind OneWeb. As a company, we have some of the best-in-class investors in the world. We have strategic partners ranging from Airbus, Hughes, Eutelsat, SoftBank, just to name a few. We recently announced a merger with Eutelsat, a well-known European satellite communications company. We continue to innovate in space. We just had our latest satellite launch happen just a few days ago. That carried 16 production satellites as well as one test satellite for the next generation of satellites for OneWeb. So, you know, our current constellation has 648 satellites, which will completely cover every corner of the Earth. But as you know, low Earth orbit satellites, as with any satellites, there is a limited lifespan, and low Earth orbit satellites like OneWeb have a lifespan of somewhere between 6 to 8 years. So we have already started planning for our next generation of satellites. But our next generation of satellites is going to have not just the basic connectivity capability, but all the latest in satellite technology built into it. We have been working with the European Space Agency as well as the UK Space Agency to include a number of new technologies, which I can't talk about all of them today, but just to give you an example, like the beam hopping capability, so that we can easily allocate power where and when it's necessary. So these are some of the new technologies that are being built into the next generation of OneWeb satellites. So we have launched one such test satellite together with the 16 production satellites that we need to complete our constellation. So that being said, now technology, as the user will see, is not going to be that different regardless of who is providing you and what we are operating in space. Because when you sit inside your house and you're accessing the internet, it's very hard for you to tell if this is coming from, you know, operator A, operator B. Of course, you will be able to tell from the difference in latency and that sort of stuff. You can say if it's geostationary or LEO. But once you come to the LEO segment, there may be multiple operators in this space who can probably give you the same sort of service. So how is OneWeb different? We have painstakingly made sure that we can actually fit into our downstream partners and our network partners as value chain. So we're not trying to become Philippines' fourth telco, for example. It's not our goal to go and reach every home with our own terminal and become the leader in, you know, connecting every home in that way. However, we have the technology that is capable of connecting every home, but we work as a B2B solution. So we work through partners who know the local market and the local regulations and the local requirements way better than we do. So in the Philippines, we will be working with a number of local partners who have all of the regulatory clearances and the understanding of the local requirements. And then they will be the ones taking care of your requirements on the ground. We make sure that they have the tools, they have the technology, they have the coverage, so they can do that in every corner of the Philippine archipelago. So why I say that is to highlight the point that the structure of the OneWeb network is like a IP local loop in space, which means we think about every aspect of how the user is going to want to use our service. So they, at the very low end, you could be looking at people who simply want to browse the net, send emails, make some WhatsApp messages and calls, and that's it. That would make them extremely happy. But at the other end, you may have people who are operating application to application connectivity, machine to machine connectivity, where latency is very important. There may be some voice traffic combined with some IoT traffic. So expedited forwarding, assured call forwarding, all of these things become very important for certain enterprise customers. If we just gave them a consumer grade product and say, now you go figure out everything else, we're not going to be a B2B solution. So we have decided as a network to make sure that what we offer to our partners is flexible and dynamic enough so that they can deliver the service that their end customer wants. So the end customer can be a simple a user sitting at home browsing the net. It can be a school that's downloading large amounts of their education syllabus, or it can be a bank that is doing a lot of online, machine to machine transactions. It can be a defense customer. It can be a hospital. So that's our goal. Make sure when we say it is a system that can serve everyone everywhere, we actually mean that. Everyone has to include not just every individual at home, but every system, every business that needs the connectivity. We have already signed up, in keeping with what I just told you, that we don't go directly to end customers, but we work with partners. As you can see, there's a long list of reliable and trusted partners who have already signed up with OneWeb. And there is, for every one partner that is on this slide, there is another 2 or 3 still talking to us and getting their deals finalized with OneWeb. So when we finish, with the last launch, that happened a few days ago, we now have all the necessary satellites to fully cover the globe. The next thing, of course, is, we can't just serve, provide you enterprise grade connectivity just with satellites. We also need ground networks, gateways on the ground, points of presence where our customers can connect, and a whole range of digital products to make it possible for our partners and their customers to enjoy the service without any hitch. So that is the next phase. Not so much the next phase has been happening already, but we aim to complete that entire rollout, not just in space, but also on the ground by the end of this year. So by the end of this year, you will have full connectivity to the OneWeb network from every corner of the Philippines, as it will be from Southeast Asia, Indonesia, Australia, anywhere in the world. Okay. So in connecting our partners, what we also do is to make sure that they are able to meet the requirements of their customers. So OneWeb connectivity comes with service level agreements, committed information rates, and various guarantees to make sure that if you're in the business of providing ISP services or local sort of satellite connectivity, I'm sure your customers will basically ask you, what quality of service are you providing? What sort of availability? Can you provide us 99% availability? Can you provide us this kind of CIR? So in order for them to be able to support such requests, we have also made sure that our system can support all of those SLAs, CIRs, and various guarantees that the end user or the business that is using OneWeb requires. What I'd like to do now, just to skip a couple of slides from here, because of course I'm more than happy to share this information with you. But basically, from a user perspective, what becomes important is how do you see the LEO reliable connectivity that OneWeb is going to bring actually work in the community? How is it going to work on the ground? So I'll give you like 2 or 3 examples. One is cellular backhaul, right? So you have a lot of cellular networks, you know, in the Philippines, and there is the latest one, Ditto Telecommunity. They're rolling out very fast. So when you're rolling out networks, you need a lot of base stations, and the base stations somehow need to be connected to the center of this the network. So at the moment, you have fiber and microwave, and in some cases, satellite connectivity connecting these far end cell sites to the core network. But when you do that, you still have various qualities of connection. So, for example, if you want to have 4G voice, you need to have latency not exceeding 150 or something like that. So, you know, if you use geostationary satellite, there are limitations to what kind of services that cell site can actually deliver using a geostationary backhaul. So what OneWeb does is we have come up with various plans to support different sizes of remote cell sites. So it can be a small cell site, a micro cell site that is just serving a small school community or mining community. It can also be a larger cell site that is serving a small village. So, and then the network provider can decide what kind of services he's going to deliver. And then based on that, he can then configure the OneWeb connectivity to that village to suit the cellular backhaul requirements he has. Community broadband is another example. So community broadband is the other extreme, and you don't really need, you can just instantly power up a community. In the event, let's say, you may already have connectivity, but, you know, Philippines is one of the countries, for example, that's often affected by natural disasters. If such a, God forbid, the next natural disaster hits the Philippines and you have no connectivity, if you have a OneWeb system available, then you can quickly power it up and immediately connect that local community using the OneWeb terminal and a Wi-Fi or WiMAX connection to connect the local network. We've been also connecting wind farms, local power stations, power grid monitoring, pipeline monitoring, a whole range of services in very remote parts of the world, but you need reliable connectivity. Then OneWeb's LEO satellite networks can actually be a huge help in making that happen. Now, I say we have been already connecting is because even though I told you that globally the OneWeb service is going to be available at the end of this year, because we have been gradually rolling out, OneWeb satellites are in a polar orbit, which means it goes over the north and the south poles at equal distance orbital planes. So naturally, the north and the south poles got coverage first, because as you come towards the equator, the satellites are more widely spread. Therefore, we need more satellites to cover. But in the north and the south, coverage was provided almost a year and a half ago. So we have already been serving a number of people in the very northern end of the world, the northern hemisphere, about 50 degrees north for more than a year, and then even above 30 degrees north. We have just started offering services as well. But these are not your fully fledged commercial services. So we're working with a select group of partners to make sure that the available services are used in the best possible way. I've already mentioned to you like the first responders situation, which is, with natural disasters, it is one of the key use cases that OneWeb's user terminals will be put to. The other big difference with OneWeb is, because I mentioned to you, we're in the business of making sure that our customers have a seamless and flexible and dynamic system that they can use. We have also made different user terminals to cope with different requirements. So at the very top end, I mean, physically very large terminals that are necessary to provide high quality cellular backhaul, or when you want to power up an entire mining site or a rural community, we have those parabolic terminals sitting at the top end of the slide. Then we have flat panels, which is what people like to see because they don't like these monstrous big machines sitting on top of their roofs. So we have a lot of flat panel alternatives manufactured by some of the world's leading manufacturers of flat panel antennas. Then all the way down to mobility units. So the last two antennas you see are the ones that you put on airplanes. So we can connect a remote village for basic internet access all the way up to high-speed connectivity on an airplane where you may be watching Netflix, you may be browsing the net, buying things, making all of that possible while you're traveling at over 600-700 kilometers an hour. So all of these requirements need different types of user terminals, and OneWeb's user terminal partners have already manufactured or in the process of manufacturing some of the world-leading market hardware that we need for the LEO connectivity. Then finally, the global ground network. As I mentioned to you, this is the final piece of the jigsaw. Once we have the satellites, we also need ground network, the Earth stations. Unlike a geostationary satellite teleport, OneWeb gateways have multiple satellite antennas. So, in a typical gateway in the Southeast Asia region, we will have somewhere between sort of 15 to 20 Ka band antennas that are looking into space, and they will basically be the link from the ground to the satellite. So you will be connecting to the satellite from your user terminal, like one of the ones I just showed you earlier. And then once it reaches the satellite, then it bounces back onto these ground networks, ground gateways, and from where we connect to the ground networks. And therefore you get to access to the internet or to the local network of a secure network. It can be belonging to a government or a bank or whatever the case may be. And all that connectivity is provided after the traffic lands on one of our gateways. As I mentioned to you, our satellite constellation is now complete. We have, as I mentioned before, we have our design that features a leave no trace responsible space initiative. So everything that we put up in space comes back and disappears. And on top of everything else, one of the main requirements of Connect networks today is cybersecurity. So we have multiple layered security built into our network to make sure that the traffic that goes into our network is safely and securely delivered to its destination. Finally, we're also working on the ability to combine our LEO capabilities with the GEO networks so that there is seamless interoperability between LEO and GEO networks. And there are technical and commercial applications where this is necessary, not just from a backup point of view, but also in managing the traffic loads carefully so that we can offload and onload depending on what the requirements are for latency and capacity between the two types of networks. I didn't really want to dive too much into this because I think we've more than covered enough about the benefits of low Earth orbit. But this slide kind of highlights the point that I was making earlier between the difference between geostationary satellites and low Earth orbiting satellites. The latency is the obvious discussion, but one other thing I'd like to show is the second line here. This is just below the red line that talks about supply and demand. The gray section, the second section here, which talks about mass satellite production, launch cost reduction, new usage, data consumption. I think that is also a major advantage that low Earth orbit satellite operators have brought to the satellite industry in general. because we need hundreds, if not thousands of satellites, depending on the constellation, we've had to come up with new ways of producing these satellites. I mean, for example, OneWeb satellites, which are manufactured by a company called OneWeb Satellites, is a joint venture between OneWeb and Airbus. And we make somewhere between 1 to 2 satellites a day. I mean, the time I went into the satellite industry, it took us like a year, maybe 2 years to put together one satellite. Now we make them 1 or 2 a day. It's actually like an assembly facility where we just make them day after day after day. We never stop manufacturing. We keep improving the technology that goes into it. The other thing we've had to do, and with the help of some of the world's leading launch providers, launch costs in general had to come down. And because we can pack in somewhere between 30 and 40 satellites per launch, the cost attributable per satellite to get into orbit also comes down quite significantly. So the launch costs are lower, the production costs are lower, so we can pack all of these in delivering a very, even though the service offer is way more advanced than what was available 10 or 20 years ago, the cost per megabit per second has become very much more affordable than what it used to be back in the days. So then, of course, you know, all of this is necessary to support the new usage that I already mentioned to you, where, you know, it's not just people talking to each other or people accessing the internet. There are machines talking to each other. There are cars driving by themselves. There are airplanes flying by themselves. So to provide all of these connectivity in a reliable way is why, you know, some systems like OneWeb have now come up and we plan to deliver. I'm going to stop at that and take questions from you. Was that good enough? Was that detailed enough? Is anybody still there?
All right. Thank you, sir. Thank you, Mr. Bala, for a very informational presentation.
You're welcome.
So yeah, I think we have questions lined up for you, sir. But before that, we want to thank you for having us today. We have learned a lot about OneWeb's technology and how space technology OneWeb is using and improving the lives of the people.
Thank you.
So for our first question, we have, wait, give me a second. So here's a question, sir, for you. With the space as a sort of a limited resource, do you think there will be regulations in the future on the number of satellites that can orbit at a time?
Well, that's a very good question, and I think I sincerely hope the regulations continue to evolve. There already is. There is already the regulatory framework to manage from GEO to LEO, what sort of satellites and what sort of spacing, and also there are very clear-cut instructions about how we fly these satellites so that we don't go around crashing into everything else that's up in space. But the thing is, I don't think it is enough. I think it needs to evolve. I think you also need to evolve the type of satellites and what use it is going to be put into, and in which orbits they can be, and so on and so on. So this is a ongoing debate and discussion, and I don't know if there is a definite answer right now, but I definitely hope there will be answers in the future. I agree with you. There needs to be more stringent regulations in how we manage this.
All right. Thank you, sir, for that answer. So another question is, how big is the team required to do mission control operations for LEO satellite constellations?
So OneWeb, for example, has a satellite control center and network control center in London and also in Virginia. So we back up each location with the other. I don't quite know exactly how many people we have in the satellite control center, but I know it's not. It's intense. It's not hundreds of people. It's tens of people. But it is also aided by some very highly advanced computer technology that manages it. So it's not necessarily just the number of people, but we also have some advanced computer technology and software that keeps track of every satellite and tells every satellite we know at any point where exactly the satellite is. We know which satellite is connecting, which satellites is connecting to which gateway. We know which beam within which satellite is connecting to which user. So there's a lot of detail. When you're talking about hundreds of thousands of users, it is not easily managed by individuals. So there are a lot of computer systems that take care of that. But yeah, it's a mammoth task, and it is the real rocket science end of the satellite connectivity business.
All right. Thank you, sir, for the answer. So we have a question here in the chat from Mr. Wesley Clark Silverderio. So what happens to LEO satellite constellations when their lifespan runs out?
Yeah, so we all have different ways of dealing with it. I can only speak for OneWeb. I can't really speak for others, and this is a very serious concern the entire satellite community in the world has, and it is related to the earlier question about how is it regulated, how many satellites can you have in each orbital plane, and so on. OneWeb has taken it upon itself to lead an organization or lead an initiative called Responsible Space. So what we do, everything that goes into making a OneWeb satellite will burn up upon re-entry. So we are not going to leave our satellites in a graveyard orbit. When our satellites reach end of life, there is a way to send them back to Earth and make them burn up upon re-entry. So technically, there will be no trace. I mean, physically, technically, I mean, literally, there will be no trace at all when a OneWeb satellite reaches end of life. It will burn up upon re-entry. And I think that is the least that every operator has to do, because the space is a very important resource that we all need to use and we all need to share. So we have to deal with it responsibly, and I think OneWeb is doing that. We have two features. One is, of course, burning up upon re-entry, and the other is we have also built into our satellites a grapple capability. So if there is a rogue satellite that that needs to be brought back in control, then there is also we can send other vehicles to capture it using the grapple capability.
Nice.
So there are multiple technologies built in. Don't ask me exactly how these things work, but I know they exist to make sure that everything comes back safely.
All right, sir. Thank you for that wonderful answer. So here's another question, sir. Oftentimes, typhoons pass through the Philippines. Does thick cloud cover or the extreme weather conditions affect the performance of the communication link to the satellite constellation to user terminals?
So again, a good question. You have, as with different connectivity communications bands, there is likely degradation of link quality when severe weather hits. And there are technologies already in place, even in the geostationary world. When you're faced with inclement weather, how do you actually keep the communication links up? So there are various methods of managing the power that is transmitted from the gateway to make sure that the connection remains intact. But one of the key features that OneWeb, and generally in low Earth orbit systems, this is an advantage, is that we are much closer to the Earth. Therefore, the power levels are significantly better than what you'd experience from a geostationary satellite. And then on top of that, there are multiple satellites with multiple look angles to the user. And therefore, we're not always directly above the user for a number of reasons, especially in the equatorial region. We can't do that in order to avoid interference with geostationary satellites. So because we'll be looking at it from an angle, and also because we are closer to the Earth, and because we are, we can look at it from multiple angles, we have been able to simulate, like even in rainy conditions, over 98 to 99% availability throughout the year. So it is, it's simulated. We know that we still need to put it to the test, but we are confident that we will be able to ride through severe weather without too much interference. I'm not saying there'll be no drop at all. I think if you're in the KU band connectivity space, you will be affected by weather. But I think it's going to be a lot better than what you might have experienced with geostationary satellites.
Yep. Thank you, sir. So a part of the audience right now, sir, are students. So what kind of background, college course, or would I need, for example, to have if I want to land a career in the LEO internet satellite industry? Or like I want to apply with OneWeb?
That's a very good, it's a very good question. I just don't know how to answer because, back in the days, I used to work for, one of the bigger telco company names that you mentioned in the introduction, and there was a very smart lady who was in charge of communications, marketing communications, and she had a PhD in polymer science, and I was like, how is that even possible? What's the connection from polymer science to marketing communications? And my personal background, I'm finance trained. I'm an accountant, and then I went to do a master's in business administration, and I've ended up in the satellite industry. So I think depending on the role that you plan to achieve in a company like OneWeb, there is scope for all sorts of backgrounds, training. It is not just the engineers that make this company work. There are regulatory people, there are lawyers, there are business people, there are accountants, there's a whole range of people that need to come together to make a system like OneWeb work. But from an engineering point of view, I'm assuming that's the leaning of the question. There are electrical engineers, electronic engineers, computer scientists, mathematicians, all sorts of people who work in OneWeb. Some of the degrees, I don't even know what it means, but there's such complex technical degrees. But yeah, if you're really interested, you should just go to the OneWeb website, look at the jobs available, and throw in your CV, see what happens.
All right, sir. Thank you very much. So I think we are down to our last question for you, sir, today. So the question is, what is your opinion on the concerns astronomers have in the impact? What is your opinion on the concerns astronomers have in the impact of satellite constellations on astronomical observations?
I mean, it is true. I have an application on my mobile phone called Night Sky. This application used to work very easily back in the day when I could just look at every star and every planet. Now, in between, I see lots of Starlink satellites that keep popping up, and that is just looking at it from an app. So for astronomers who are watching these things, if you're not careful, you think there are meteors flying around everywhere, right? So I honestly don't know. I think it is a problem we need to manage. Maybe it's in the designing of the satellites. Maybe it's in the orbits that we permit. For example, you won't be able to see a OneWeb satellite because it's too far out in space. But because OneWeb satellites are at 1,200 kilometers, you will not be able to see it with the naked eye. So whereas those satellites that are you will be able to if you use a powerful satellite, but a powerful telescope. But if you look at those satellites that operate closer to the Earth in the 200 to 500 kilometer range, yes, they are visible, and it is a problem. I mean, I like clear skies myself, and it is annoying when these things interfere. I honestly don't know how to answer that question. I think the answer lies somewhere in the earlier question. How do you regulate how many satellites and how should they be designed? Should they have any reflective capability? Should they have some way of staying dark so that it doesn't interfere with astronomers? Maybe different ways to look at it. Very good point. Very good question. I had just don't know how to answer it. It's annoying if you're an astronomer to be interfered with this way. Yes.
All right, sir. Thank you very much.
Thank you.
Okay.
All right, I guess that ends our Q&A for Mr. Balamurali. Thank you very much for your time and expertise. I'm sure this
Thanks,
was a
John.
very interesting topic, especially for us Filipinos who are dying to have satellite internet connectivity in all of our islands here in our archipelago. And as mentioned earlier, the Philippines is an archipelago, and satellite internet is just one of the ways that technology, space technology specifically, is being used to bridge all of these islands and to connect everybody here in our country. So thank you very much for your expertise.
Thank you.
Can you still stay with us for a bit so that we could take a photo with our
Sure.
previous speaker, Sir Alfred
Absolutely.
Donald Perez? Okay, so we have a photo. Can we have a photo of Draylen? Can you come back here? Also, some of the organizers of the SIICaP team. All right. So, Mr. Rain, please take a photo of the organizers that are here online with us today.
Stand by. Okay, everyone ready?
Ready?
Hold your smiles. 3, 2, 1. Here we go.
All right. Thank you very much to the
Thank you.
SIICaP organizers and to our speakers for today, Mr. Alfred Donald Perez of ABS and Mr. Bala Morali from OneWeb. Very informative topics, very relevant to our country, especially today. So thank you very much. And we hope to see you again in future engagements with the Philippine Space Agency. So
Thank you.
to our audience, don't fret. We still have a few more items in store for you. So, Draylen, go ahead.
Yes, before we end the program, we prepared a quick game for you guys. So with us is Engineer Vench Angulo from the Space Mission Control and Operations Division to facilitate the game. So good luck to the participants.
All right. All right. Can you hear me? All right. So good afternoon, everyone. So we had a very interesting afternoon because of the discussion regarding geostationary satellite communications and low Earth orbit. So to test that, if you gain some knowledge, let's have some quick quiz using this online tool, Mentimeter. I'll share my screen first. All right. All right. So can you see my screen now? So to join, kindly scan using the QR code or go to menti.com and enter the code 4763 and 4748. Yeah. So scan the QR code, and when entering, kindly use your first name and last name so we can monitor who will be the winner of this game. We have prepared some prizes. We will coordinate with you what will it be. All right. So later on, if we have determined the winners, we want you to screenshots to send you a screen capture of your screen if you are the winner and send it to the organizers. As of now, we have. All right. So let's wait for a few minutes before we start the game. Okay. Already have 28 players ready. 31. Please use your name, your first name and last name in joining. We can determine who will be the winner. Right. So I think we are ready. Let's start the game. Answer fast to get more points. For the first question, blank is a regular path that one object takes around another object. Blank is a regular repeating path that one object in space takes around another. One has voted. Correct answer is orbit. So let's see the leading one. Right. The leading one is genetics fastest, 181 points. Okay. So all others, get luck next time. We have a few more questions. Question number 2. Answer fast, get more question. Second question. Geocentric orbits with altitude below 2,000 kilometers. What is this geocentric orbit with altitude below 1,000 kilometers? 6, 5, 4, 3, 2, 1. Time is up. Correct answer is full Earth orbit. It's geocentric orbit with an altitude below 1,000 kilometers. Third question. Okay. Answer fast to get more points. Orbits that has zero eccentricity. What is this orbit that has zero eccentricity? Is it elliptical, circular, or sun-synchronous orbit? Correct answer is circular orbit. 26 got the correct answer. Other 15, better luck next time. Question number 4. We have 46 players left. Mechanical parts that control hardware of the satellite, like solar array, antenna positioners, and gyros. Is it power subsystem, mechanism subsystem, or the payload subsystem? 3, 2, 1. Correct answer is mechanism. So mechanism subsystem is the mechanical parts that control the hardware of the satellite. Let's see the leading one. So our top one is Joe. Next is Lucelu and Zonatics on the third spot. Next question, fifth question. This one produce forces and torques to modify satellite orbit to support attitude control. This subsystem produce forces and torques to modify satellite orbit to support attitude payload, attitude control. Correct answer is propulsion subsystem. 15, that's the correct answer. Question number 6. Maintains satellite pointing orientation in all 3 axes. This is another subsystem of the satellite. It maintains satellite pointing or orientation in all 3 axes. Is it a thermal subsystem, attitude control subsystem, or the power subsystem? Correct answer is the attitude control subsystem. He was leading. Leading with 5,729 points is still Joe. Next is Bianca and Gilbert Alvi. Right. So, kaya pa nating humabol. We still have 3 more questions to go. 7th question, the orbit control process required to maintain a stationary orbit. Is it cross-pole isolation, satellite maneuver, or station keeping? The orbit control process required to maintain stationary orbit. Cross-pole isolation, satellite maneuver, or station keeping. The correct answer is station keeping. So that's the orbit control process required to maintain stationary orbit. Discussed by Sir Alfred. Question 8. What is the main advantage of GEO communication satellites over geostationary satellites? Larger coverage area, faster communications, better operational lifespan, better resistance to atmospheric surface. Is the main advantage of GEO communication satellites over geostationary. The main advantage is it has faster communication speed because it is more near to the stationary orbit. Okay, who's on top? Joe is still on top. Next is Frosty and Ian Lagnat, the third spot. Question number 9. How does a LEO communication satellite achieve global coverage? By maintaining a stationary position above the equator, by reflecting signals on the surface, by using multiple satellites in the constellation, by transmitting signal through underground cables. Correct answer is by using multiple satellites in the constellation. The last question. What is the purpose of satellite telemetry? A, to control the satellite operations and functions, transmit live video feed from space, or to monitor satellite health and performance. Correct answer is to monitor satellite health and performance. So, B was the top 3 winners. Our top 3 is top 1 is Rogelisa Taclobo, second is Joe, and top 3 is Enzo Mendito. To the 3 winners, kindly screenshot your screen and send it to the organizer so we can give your prize. Thank you very much. That's all. I hope you enjoyed the game.
All right. Thank you, Sir Bench. And for everyone who participated in the game, congratulations. So I hope you enjoy your prizes and please wait for it. So we would like to take this opportunity to thank everyone for supporting SIICaP. We wouldn't be here without your support. And to conclude our webinar for today, we would like to welcome Dr. Israel Zenar Bautista of the Space Mission Control and Operations Division. Hello, Sir Izzy.
Hello, good afternoon to everyone once again. So to everyone who have joined us in our SIICaP webinar, and to our esteemed experts, I would like to express my sincere gratitude for your continued support to the Philippine Space Agency and our event Space Information Infrastructure Capacity Building and Training Program, or SIICaP. Our experts discussed a lot of things, so thank you, Sir Alfred and Sir Bala, for being very generous in sharing your knowledge and expertise in operating commercial satellites both in the GEO and LEO orbit. Thank you for shedding light about the satellite technologies that you are using, and we are always using these technologies to keep us connected with each other. So from satellite subsystems to ground station operations, satellite relocation or orbit transfer and transponder technology, and the various applications that we use satellite communications. We have learned a lot today, and we hope that these advancements in technology would continue to help our country in moving forward and for all the Filipinos to benefit from. Thank you to our attendees for your very active participation, asking questions, and showing enthusiasm, albeit virtually. This elevated our webinar's quality for today. As we close this webinar, we hope that you have learned and this would serve as inspiration to you to continue learning about satellite technology and space and how it can be used to continue improve lives of our fellow Filipinos, overcome challenges, and unlock new opportunities. Thank you once again for joining us and for your very active participation. May you have a great day ahead and see you in future SIICaP webinars and other future PhilSA events. Thank you.
Thank you very much, Dr. Izzy Bautista of the Space Mission Control Operations Division. So before we send the evaluation link for us to know how well we did during today's webinar, may we ask for a photo opportunity with you guys? Please turn on your cameras if possible. This is for everyone now. This is for all of the participants of today's SIICaP webinar. Let's wait for everybody to turn their cameras on. Wow, it's great to see so many faces today. I think we have representatives of students, government employees. I think we also have private company employees. All right, let's wait for a little bit for everybody to turn their cameras on. Please note that these photos may be shared on our social media pages. So if you're not comfortable showing your faces on our social media, feel free to not turn your cameras on, but we'd love for everybody to please be here. And let's wait for like 10 more seconds for everybody to be here. Okay, I think we're ready. Ayan pa, may mga humahabol pa po. All right, Mr. Rain, our resident photographer.
Stand by, everyone. Smile in 3, 2, 1. There we go. Thank you.
All right. Thank you very much, Rain, and thank you to all of our participants for today's SIICaP webinar. And that's it for our webinar today. For the participants, please accomplish the evaluation form for you to receive your certificates of attendance. So the link is sent on the chat box, and we also have the QR code for those who are on their phones and could just take a photo of the QR code. Please answer so that you will receive your certificates of participation, certificate of attendance for today's webinar. Thank you for joining the mission, and please continue following the PhilSA journey. Please visit our website at philsa.gov.ph and follow our social media pages for updates. Happy Friday!